Okay, it's ready to go. So it's on the hour. We can, you can start, Matthew. Go ahead.
Okay. Is there a way I can see how many participants we have? Yes, I see. We have some attendees here. Wonderful. Okay, we're going to wait about another minute to let people filter in, but welcome everybody to the District Energy Systems Modeling webinar. Okay. Okay, well, I think I'll go ahead and get started. If you're filtering in a bit late, you should be able to watch the recording as this is being recorded. So welcome everyone. So this is the District Energy Systems Modeling webinar. We have two excellent presenters today. First, we have Amy Allen, who is one of my colleagues at the National Renewable Energy Lab. Amy joined NREL in 2018. Her work focuses on modeling grid interactive efficient buildings. And she completed her doctorate in architectural engineering at the University of Colorado Boulder. And prior to joining NREL, she worked as an engineer at KW Engineering in Oakland, California. Our second presenter is Bharath Karambakam, who brings over 16 years in building simulation experience for code compliance, lead credit termination, and payback analysis. So his project experiences include offices, healthcare, universities, and sports facilities. And that includes analysis of advanced HVAC, renewable energy storage, and fully electric heating systems. So I'd like to get right into it to our presenters. So our first presenter is Amy Allen. So Amy, take it away.
Okay, thanks very much, Matt, for inviting me to speak. And I'm sorry, I'll just make sure that this is advancing as expected. Okay, thanks. As Matt mentioned, I'm an engineer at the National Renewable Energy Lab, and today I'll be giving a presentation on some design and evaluation considerations related to ambient loops, which are an advanced form of district thermal energy systems. You may be familiar with the steam or chilled water systems that are commonplace on university campuses and some dense urban areas throughout the US, and even more common in Europe. This schematic graphic shows how district thermal energy systems have evolved over time to use water rather than steam as a working fluid and to provide cooling as well as heating, and to use water at increasingly moderate temperatures, leading to the moniker of ambient loops to describe emerging forms of these systems that use water at temperatures very close to air temperature. And this figure from a paper by Lund and others in 2014 shows qualitatively how the use of water as a working fluid and water at increasingly moderate temperatures has improved the energy efficiency of these systems. And Lund and others have often characterized the evolution of these systems into either 4 or 5 generations. And I'll use the nomenclature from a paper by Buffa in 2019, which characterizes these systems into 5 generations, with emerging 5th generation systems operating at network temperatures between 15 to 25 degrees Celsius and leveraging water source heat pumps at connected buildings to further temper the water to meet the building's heating and cooling loads. And several factors allow these systems to operate more efficiently than the steam or chilled water systems common in the past and still in use today. And that includes the reduced distribution losses associated with the more moderate temperatures, as well as an improvement in primary equipment in terms of exergy by using sources that are well matched to the network temperatures. And this facilitates the use of heat pumps as opposed to boilers to provide both heating and cooling, which is also compatible with electrification of source energy, which advances decarbonization goals as electricity increasingly comes from renewable sources. And these more moderate network temperatures also facilitate the use of renewable thermal sources, such as solar thermal, and also the beneficial use of so-called waste heat sources, such as heat from data centers or commercial refrigeration. And these more moderate temperatures expand the range of waste heat sources which are useful in this context. There are a variety of examples of existing fifth generation district heating and cooling systems in the US and to an even greater extent in Europe. And I'll describe a few of these examples and feel free to chime in if you're aware of others. Both Colorado Mesa University and Weber State University in Grand Junction, Colorado, and Ogden, Utah, respectively, have fifth generation district heating and cooling systems that are tied to ground heat exchangers at the district level to reject and draw heat from, with individual buildings being conditioned by water source heat pumps tied to this loop. And ground heat exchangers are advantageous for fifth generation systems because at a district scale, heating and cooling loads from connected buildings can balance each other out at a variety of time scales, both daily and annually, which can mitigate the effect observed in ground heat exchangers tied to individual buildings of heat building up, so to speak, over time due to an imbalance of heating and cooling loads. And this synergistic sharing of heat or heat rejection, so to speak, also improves the efficiency of ambient loops by allowing buildings to operate as prosumers or producers and consumers and offset each other's heating and cooling loads, which reduces the load on primary equipment to condition the loop. And in addition to these university examples, residential development near Austin, Texas, called Whisper Valley, leverages a ground heat exchanger tied to a district loop and water to air heat pumps at individual buildings to provide space conditioning. And the initial phase of development at Whisper Valley consisted of about 200 homes, but the development is planned to extend to almost 7,500 houses and a commercial development as well. In Massachusetts, there are currently several utility pilot programs underway, in addition to one overseen by the State Attorney General Office, to implement a so-called geogrid system, which is similar to what I described in the other applications, with a ground heat exchanger tempering a shared water loop, providing conditioning to buildings conditioned by water source heat pumps. And this application is focused on a retrofit to avert the need for upgrades or replacements to existing natural gas infrastructure and replace that entirely with a water loop conditioned by ground heat exchangers, with building equipment then replaced with electrified space heating and domestic hot water heating, and electric dryers and cooking equipment to replace gas versions of that equipment. And thus to facilitate full building electrification as a way of advancing decarbonization and also addressing leaks and safety concerns associated with aging natural gas infrastructure. In Europe, numerous examples exist of fifth generation district heating and cooling systems in different forms. And two that I'll highlight are on the campus of ETH Zurich in Switzerland and the so-called mine water development in Herleen in the Netherlands. The ETH Zurich campus is conditioned by a fifth generation district heating and cooling system tied to ground heat exchangers and separated into several grids or clusters of buildings, which can exchange heat both among themselves and between grids. And the ETH Zurich system also incorporates seasonal storage through a water and ground heat exchanger system, which further facilitates balancing of heating and cooling loads among connected buildings and over the course of a year. And this system of intersecting grids also allows sections of the grids to operate at different temperatures. The so-called mine water system in the Netherlands leverages water that has flooded abandoned mines as a source for heating and heat rejection, and has evolved over time from a so-called fourth generation system operating at higher temperatures in heating and lower temperatures in cooling to an ambient loop operating at close to air temperature. And the various forms of these systems illustrate how building loads can synergistically offset each other and leverage ground heat exchangers and also surface water heat exchangers, as well as systems like mine water in the Netherlands to provide conditioning for the overall loop. And I'm sorry, I'll adjust this to make sure the whole slide is showing. In this diagram and the one on the next slide, I'll show in a bit more detail different configurations of ambient loops. And there are two canonical forms that can be distinguished by whether or not bidirectional mass flow can take place in the main loop. And this diagram illustrates a form in which that is permitted. And so this design facilitates both bidirectional thermal flow, as reflected in the fact that connected loads, such as the two shown here, will either reject heat to or draw heat from the main loop, depending on the building's dominant load, which in this case will also be reflected in the dominant direction of mass flow in the loop, meaning if there's a dominant heating load in the loop as a whole, the direction of mass flow will be from the so-called warm pipe to the cool pipe, and vice versa if the dominant load is cooling. If the connected buildings exactly balanced each other in load, then there'd be no mass flow through the centralized heat pump, and the building's complementary loads would simply offset each other. And in this example, the delta T across each connected buildings is controlled to around 6 degrees C, with the warm pipe operating in the range of 20 degrees C and the cool pipe operating in the range of 14 degrees C. And in systems of this nature, there's often a range of acceptable temperatures on each pipe or in the network as a whole. And shown here are water source heat pumps conditioning the building, and also circulation pumps drawing water from either the warm pipe or the cool pipe, depending on the load conditions at the building. And work by Vetter and Hu, and also a study by Sulzer, which was focused on the 5G DH system at ETH Zurich, has revealed practical problems in control of circulation pumps in systems with this two-pipe configuration, which veteran who decided resulted primarily from conditions of low load at the connected buildings, in which case a control valve would modulate to reduce the minimum flow from a circulation pump, which is likely oversized, which could result in control instabilities propagating among the connected loads since they are hydraulically coupled. And there exist ways of mitigating this problem, including with the use of bypasses at connected loads, which aren't shown in this diagram, though the use of bypasses can increase the infrastructure cost and limit the easy extensibility of systems of this nature. And the extensibility consideration is important in existing developments that are likely to be extended and also potentially in new developments. This diagram shows an alternate configuration of a 5G DHC system in which a single pipe serves the entire network and through which water is circulated, which is used for both heating and cooling. And in this case, if inlets and outlets for the connected loads are located close together, there's a minimal or negligible pressure differential across each connected load, which allows them to be hydraulically decoupled from the main loop and can mitigate the potential pressure control instabilities at low load conditions. And the network temperature in this case can float in a similar range of 15 to 25 degrees C or so. And this network configuration does result in penalties in terms of exergy destruction and thus also higher energy use through the lack of separation of heating and cooling loads, in that buildings are both rejecting and drawing heat from the same side of this loop, so to speak, since it operates with a single pipe. An analysis by Sulzer for a particular set of conditions found this penalty to be minimal, but the nature of the benefits of a two-pipe versus one-pipe configuration are also somewhat context dependent. And I'll also note that there are other design configurations possible as well. These are just somewhat representative examples of two main categories of these systems, so to speak. And it's important to note that both of these system configurations reflect bidirectional thermal flow in terms of connected loads, both drawing heat from and rejecting it to the network. The work that I carried out for my dissertation involved analysis of several case studies of prototypical districts conditioned by ambient loops. And I'll discuss some of those results here, both in terms of energy and economic performance of these systems at an individual building and at a district level. I considered one case study district consisting of 5 prototypical buildings based on the US DOE prototype building models, and considering those with their independent systems, which are shown in this table at right, and also in a case in which I modified the building level HVAC systems to be compatible with an ambient loop. That is, to use water source heat pumps tied to a moderate water temperature source for space conditioning. And I considered an ambient loop operating in the two-pipe configuration similar to the ones shown on an earlier slide. And as part of this analysis, I disaggregated the space conditioning energy use associated with circulation pumps and a centralized ground source heat pump serving the loop to the individual buildings, in addition with their own water source heat pump energy use, and compared that on a site and source basis to the EUI associated with the independent systems. And note that the independent building systems used natural gas for heating. And particularly in the case of the prototypical hospital building, the use of the ambient loop and electrified space heating systems resulted in a significant reduction in site energy use and also in a reduction in source EUI. And the electrification of heating contributes to the greater reduction in site EUI. And in this case, this was largely attributable to the fact that the prototypical hospital building had significant load diversity within its own zones, and thus its own water source heat pump loop, such as those that are used in buildings with independent systems, also allowed for a significant amount of load sharing, and thus a reduction in site energy use intensity relative to the independent systems. And this ambient loop configuration did not result in a great deal of heat rejection or sharing of heat among buildings, which I can discuss in more detail if there's interest. But it did result in a significant EUI reduction for this individual building type. And because of the dominant nature of the hospital building's load, that also resulted in an overall EUI reduction at the district level, which points to the benefits of these systems for individual buildings and districts in which significant thermal load diversity exists. And I selected these prototypical building types based on a load diversity metric on an annual basis that was proposed by Zarin Pass and others in a 2018 paper. And as one can imagine, higher levels of thermal load diversity at an individual building or a district level enhance the potential benefits of ambient loops. To highlight the reductions in EUI at a district level, this plot shows results from a larger prototypical district consisting of a different combination of buildings that were again based on the DOE prototype building models. And this box plot shows the range of source EUI as a function of the number of buildings connected to the network. And of course, the exact combination of buildings varies within a given vertical line of the box plot. But the overall trend is very clear in that the greater extension of the network within this prototypical district enhances the energy savings benefits of the ambient loop. Because once again, the ambient loop offered benefits in individual building HVAC EUI, and these benefits were also extended across the district as a whole. And this particular combination of buildings was selected based on the value of a load density metric that's often used for screening of conventional district heating systems. And in the context of ambient loops, can indicate viability at lower levels of load density, since these systems can leverage uninsulated plastic pipe, which lowers the infrastructure costs, and also through the benefits of synergistic load sharing among connected buildings, can offer energy efficiency benefits at lower overall load densities than conventional district heating systems would. These plots show overall life cycle cost performance of various network configurations serving the two districts described previously, with the results related to the smaller district shown in the plot at left and the larger district shown in the plot at right. And I'll try to describe this briefly for the sake of time, but I could elaborate more if there's interest. And that is to say that in both of these cases, a trend was observed that a particular building's connection to the loop drove the energy savings benefits and also the cost savings benefits associated with the use of a network. And the higher cost associated with electrified heating as opposed to heating through natural gas, as is the case throughout much of the US, hamstrung the ability of electrified space heating systems to compete on a life cycle cost basis, though they offered sometimes significant benefits in reduction of source EUI. And the life cycle cost metric that I considered in this analysis included a potential future price on carbon, which of course isn't currently a policy metric in the US, but serves to financially account for the benefits of carbon emissions reductions through the use of electrified heating. And I've highlighted here a few considerations for design and evaluation of ambient loops and the sort of data that can be required. As mentioned previously, load density and diversity metrics are useful in evaluating the viability of ambient loops from both an energy and life cycle cost perspective. Potential locations for centralized equipment, if applicable, such as ground source heat pumps or heat exchangers located in bodies of surface water, should be considered. It's useful to characterize potential waste or renewable thermal sources that could be integrated into such a network. And since these systems entail the use of thermal networks, which are generally located underground, it's also important to consider locations of existing underground infrastructure. I'd also like to highlight a tool that can be leveraged for design of ambient loops and other district thermal energy systems, which is the Urban Opt software development kit developed by NREL and its partners, which leverages the Open Studio and Energy Plus modeling ecosystem for modeling building loads, and also the work of commercial partners in developing modules for facilitating user interaction with the software development kit, with graphical user interfaces, and also analysis modules to facilitate analysis and design of renewable distributed generation systems at the district level, and also analysis of grid interactivity and evaluation of energy efficiency and demand response measures in that context. And I'll highlight one module of Urban Opt in particular that's of interest in this context, which is its District Energy Systems module, which leverages detailed models in Modelica, specifically component models in the Modelica Buildings Library, as well as additional custom models that have been developed as part of this work to represent the thermal network, primary equipment, and energy transfer stations to connect buildings to the network, as well as leveraging several types of building load models, including the spawn of Energy Plus, reduced order, resistor capacitor network models, and time series thermal loads, which can be generated through the Urban Opt software development kit, or provided externally, such as from data corresponding to existing buildings. And work is underway to extend the use of the District Energy Systems module in Urban Opt from fourth generation systems to reflect both older generations of steam systems and ambient loops operating at close to air temperature. I'm sorry. And I'll briefly highlight some relevant research questions related to ambient loops. And those include network topology optimization, since the more moderate water temperatures facilitate consideration of a wider search space of network configurations that can facilitate synergistic sharing of heat and heat rejection among buildings. The optimization of different operating parameters, such as network temperatures, is an area of ongoing work. And also optimal integration of waste heat, both spatially and in terms of temperature, and practical considerations such as pump control approaches to mitigate some of the control instabilities discussed previously. And here are some selected references to highlight. And for the sake of time, I'll stop there, but thanks very much. And I'm happy to answer further questions.
Excellent. Thank you so much, Amy. So if you have questions for Amy, you can use the question and answer feature at the bottom of your screen in Zoom. And we'll have maybe some time at the very end to answer questions if they aren't already answered. Okay, so let's switch over to Bharat as our next presenter. Thank you.
Can you see my screen?
Yes, we can.
Hi, this is Bharat Karambakam here. I work for IMAG as a building performance consultant, and I've been in this business in various capacities for over 16 years. So we switch over to renewable systems conversion and optimizing your system for renewable systems service and stuff. So we'll look at the factors to consider while sizing renewable energy, the central plant electrification, and we look at a good and renewable energy sizing software, and then we look at a couple of samples for renewable energy systems sizing. So essentially, when we are considering serving renewable systems, first thing you want to look at is try to optimize your investment. And to do that, we got to look at the load reduction first and see if there is any inefficiencies within the buildings, and do some kind of a retro commissioning and energy efficiency study, so your investment dollars can go as further to serve the building with renewable energy. We look at then the next step is to converting your systems depending on the goal of the project, whether you want to go for all net zero or reducing dependence on fossil fuel and reducing dependence on power on your utility grid. So those kinds of considerations, you can convert your systems to central plant systems to some kind of electric source. And then the step 3 is to really look at the source of your energy source of a grid. I mean, if your grid is already clean, and if your goal is to reduce your carbon footprint, then you probably want to work with your energy provider, and not the goal is and see if your investment can go elsewhere, and optimize, have a common shared goal of reducing the carbon footprint. And then once all that evaluation is complete, you can look at what renewable sources you can leverage to reduce our carbon footprint. Yeah, so this is a typical existing systems. You might have a boiler, air-cooled chiller, or any other water-cooled chiller, and then you'll have your system serving the spaces with hand units, and you might have ventilation systems and chill beams. So the first step is to consider replacing your boilers with air source heat pumps, right? And then that way you can do some heat exchange between the cooling and heating, and convert to electricity. Then in places where you have higher loads for cooling, you might want to consider just a backup boiler just for the peak loads, and sort of the most frequent, when you have a most frequent load, consider sizing it to the most frequent heating load, and any peak loads you can consider converting using a backup boiler. Or For the next step, I mean, depending on the funding and available funds, we can look at using a heat recovery chiller, and if the building operation permits, and there's simultaneous heating and cooling load in the building, we can evaluate that and consider heat recovery chiller. And if the building also has a lot of domestic hot water load, you can consider a heat recovery chiller to take care of the cooling load and use the hot water for your domestic hot water to serve your domestic hot water load. Yeah, when we look at the campus converting the renewable energy for entire campus, we want to look at the entire campus as one system and not look at individual buildings. So in this, you may have an administration building that has high load, but you may have parking space elsewhere that has a lot of space on the roof where you can put solar. So it's important to consider the whole campus as a system where you can balance out the space available with the load to try to achieve a high penetration of renewable energy. Yeah, we look at we come to some renewable energy evaluation software. We use a software called HomoGrid that can do some complex if systems evaluations, optimizations, and stuff. So typically, when we size the system, we might use something like a PV watt calculator that you can look at the whole total kilowatt hour generated by the renewable energy and offset the electric load. But that sort of misses a lot of aspects of the analysis. So a software like HomoGrid, what it can do is it can match the hourly load with the generation. There may be times when you have enough generation, but there's not enough load. So it'll account for uncertainty in weather if you have cloud cover or rain days and stuff. So it can put in some probability to account for weather conditions. It'll account for your time value of money. If you want to do a 25-year payback analysis, it'll account for your demand rates and utility consumption. So it'll optimize your renewable energy size in a way that you reduce your demand costs and not just looking at the energy consumption rate. So yeah, and it'll also consider net metering. And if your utility grid offers net metering, so it'll account for that to come up with the optimum size. So we move on to an example project, a couple of example projects that we did. So this one is a medical office building that wanted to evaluate what kind of PV systems that they should go with. They had a grant of about $3 million to put into renewable energy. So we started off with creating a building energy model for the building. And since this is a medical office building, you see that there's some pretty good amount of load in the night as well. So we looked at, the electric utility cost would be around $222,000 per year. And then, so if with the $3 million investment, considering the rates at the time, we could have purchased a 1200 kilowatt array. But if you look at the PV energy generation, you can see a lot of times the PV is able to generate the outputs, but we are not able to utilize it. The green bars here showing the PV outputs. The blue bars here showing the load, and the light blue ones showing the grid purchase. So, and you can see, I mean, during the weekends, you do have some PV output, but there's no load. And there are other times like this one, you have the PV is not able to output because of some weather conditions. So during those times, we'll have to get power from the grid. So those kind of evaluations can be performed with the Homer software. So in this case, by putting all the money in your just the PV, you have an output. 25% of your output is lost if the grid is not, if the utility company is not buying back any power. So so then we look at, instead of putting all the money in just the PV, if you look at a combination of PV and battery, the software will then optimize the energy supply in a way that your demand costs are reduced, and you can reduce the electric demand from the utility. So in this case, you can see the software is considering PV production, and it's charging the batteries. And you can see at night, it still considers some demand from the grid, but then it's using the batteries mostly during your morning startup, so that it can, when the solar is not available, but your grid, but your building load is high, and it's sort of supplementing the energy source from the batteries, so you can reduce your demand costs. So in this case, we saw that we see that the output lost is going from 25% to almost 6%. So there's we are able to optimize the savings by using some combination of putting your investment in a combination of PV and battery instead of all PV. Yeah, if the grid is able to, if the utility company is willing to buy back your power, that is always the best, because you're earning money for your excess output, and batteries tend to be pretty expensive. So so sending money back to the grid becomes a much more better investment. So yeah, for this project, we provided a summary of options to the client. We have the blue bars here representing their investments. The orange line here is the savings, the utility bills. And then for each of these options, the client would needed to go acquire additional land to put in their solar power. So that is also something they wanted to consider when deciding what option to choose with the PV plus battery combination. So for these 4 lines, in the last 4 options, you have all the 3 million investment constant, but the only thing that changes is the combination of whether it's all PV or PV plus battery. So if you go with all PV, you do reduce it, but if you go with a PV plus battery, you can bring it more even further. And in this case, the client went with this option, a little bit less PV and more battery. The main advantage being that the client would not need to acquire any additional land to set up their photovoltaics. We look at another example. This is a manufacturing facility that the client had. So they had several buildings used for manufacturing facilities, and they wanted to put some of the buildings had cooling and some did not, and they wanted the goal was to eventually put cooling in all their buildings, and they wanted to look at their impact on their energy consumption and what kind of solar options that they should consider, a renewable power option they should consider. So we essentially got this meter data from the client for their different buildings. Some of the buildings did have cooling, the others did not. So we looked at these buildings and we created an energy model for the whole campus with different buildings and calibrated the energy model for each of these energy usage without cooling, and then put in cooling in some of the buildings and try to match the energy consumption, usage for the actual energy usage. Yeah, these were again the different buildings that they had that we obtained energy usage data from. Yeah, so then, like I said, we created a model for their existing condition, and then we added cooling to the model and estimated their future demand, power demand, and the peak demand came close to 12 megawatt hour, and this is what we used to size our solar and renewable energy systems. Yeah, so we gave several options to the client, and with different combinations of solar and battery and wind, using a 25-year payback analysis. So a lot of these options have a pretty similar payback, but the renewable energy fraction is higher depending on the combination that they go for. Yeah, again, the client needed to consider whether they're willing to put up a windmill in their property and stuff like that. So all these, they would consider all these options to make a decision. Yep. Thank you.
Excellent. Thank you for presenting. So we have about 10 minutes or so for questions. If people would like to ask in the question and answer feature or drop them in the chat. And maybe about 20 seconds here for people to put questions in. I also have some questions, and if other people do, please ask those. So I guess a first question for Amy. So I noticed that there are differences in the kinds of grid layouts, whether they're sort of radial or a meshed grid. What tend to be the driving considerations for whether it's worthwhile to, say, put in the extra piping for a meshed grid?
Thanks for teeing that up, Matt, because I would have liked to talk about that in more detail. I just ran out of time. Some factors can relate to the nature of kind of synergistic offsetting of load among buildings, since that's one of the features that would make a meshed grid more advantageous. And if it's okay, I'll just share my screen again with that slide on it to illustrate it a bit better. I'm sorry, but yes, to Matt's point, these are kind of canonical examples of different types of grid configurations, with the radial grid being typical of older generations of district heating and cooling systems, with separate networks serving heating and cooling, and a single network path from a central plant to a connected load, whereas a meshed grid, which could exist in parallel for heating and cooling or in a single pipe configuration, provides benefits in terms of resiliency and redundancy of supply, and also can facilitate kind of synergistic sharing of heat or heat rejection among connected loads. And in the case studies that I mentioned previously, which were oriented around this network topology optimization problem, I didn't see kind of the holy grail of benefits from greater grid connectivity offsetting the higher cost associated with the network. But that's also to some extent an artifact of the grid configuration considered with parallel connections of buildings to the loop, which limits the extent to which buildings see, so to speak, a different supply temperature resulting from, loads connected at a different place in the network. And it's possible with a series network configuration in a one pipe layout that those benefits would offset the additional cost associated with the mesh network. So thanks, Matt, for bringing that up.
Yeah, awesome, thank you. So we have another question here for both presenters. So for district energy, did you look at different climate zones and what did you find? What are the considerations for the different climate zones?
Barth, do you want to start?
Yeah, for us, we looked at, this is for specific client locations that we looked at. For the PV option, it was a rural area in Wisconsin. So they had concerns about being dependent on the grid. So they wanted to try to be independent of the grid. So our analysis was based on the specific location where the client was sourcing their power from. Yeah.
And the case studies that I referenced were also for specific locations, both of them in Colorado, because they were kind of detailed analysis comparisons for those particular districts. But yes, as the person asking the question might be getting at, the balance of heating and cooling loads at different timescales, can be an important factor, particularly when designing a ground coupled system. And that, of course, would be dependent on the climate zone.
Okay, excellent. So the next question that we have here in the Q&A is for PV energy generation modeling. Is it only available weather files that are considered in terms of cloud coverage, or is it other factors?
Yeah, so the software sort of considers all the information from, it'll source data from NREL, from NOAA and stuff. So, and it'll consider a probabilistic modeling to account for potential cloud cover. Yeah, and it'll vary depending on the location and stuff. Yeah.
Okay, we have another question in chat. For consolidated historic areas with high inertia buildings, for example, European cities, do you have any experience or knowledge about the viability of domestic hot water heating district systems and their upgrades?
That's a good question. And regarding domestic hot water, I haven't extended the case studies I considered to include domestic hot water. I focused only on space heating, but certainly in general, ambient loops can serve domestic hot water, sometimes when tied to a separate grid operating at a higher temperature or coupled with a booster heat pump. And that's an interesting point regarding historic buildings and those with higher levels of inertia. And I haven't delved into that in detail, but that's an interesting point.
Okay, another question I had, it seemed that land requirements could be a concern for renewable energy systems. So particularly for PV and batteries, do you find that You install them mostly at the building level, and beyond that it's difficult, or are you seeing that there are some maybe cost savings in centralizing it on site, especially for batteries?
Yeah, so it's a combination. It depends on the location of the project. So in rural areas, land is more readily available. So they may put it up on parking lots and stuff. But when you most of the time, it tends to be on the buildings. I mean, a building roof coverage does offer a fair amount of capacity, but it depends on the layout of the building. If you have a multi-floor building in the city location, so you may need to, you may not have the space available. In those cases, they generally tend to go for recs and stuff. So yeah, it sort of depends on the location of the building. For the manufacturing facility project that I talked about, it's in a rural, it's located in rural Iowa, so they have plenty of space. So they were willing to put up the solar and the windmill.
So one last question I have, perhaps for both presenters. So it seems that with district systems, a lot of it centers on the question, is the load density high enough to be able to support those costs? And I'm curious, especially for the district energy and renewable systems with batteries. For example, with ambient loops, are they cheaper to install than other generations because you have less installation? And for renewables, is there sort of like a trade-off, especially with batteries, of where they might make less sense at, say, larger scales?
Yeah, so the load profile has a big influence on this. I mean, there are, if the load profile suits, then got to consider battery. I mean, if you're trying to meet all your energy with batteries, all your nighttime energy with batteries, it's not feasible. Batteries tend to be fairly expensive currently. So if you're just trying to limit the demand to meet your morning and evening pickup load, then and most of the day you have solar available, those tend to be the best applications. It's just to limit the peak demand a little bit, shave off the peak demand. But if you're trying to meet all your night load with batteries, that's not cost effective at the time. Yeah.
And Matt, to your point, that does seem to be the case with ambient loops relative to older generations of district thermal energy systems. And the Simone Buffa paper from 2019 compared operating examples of 5G DHC systems in Europe, and the value of that low density metric, the linear heating power demand density, and found that it was lower than the screening criteria often used for conventional district heating systems, which stands to reason, as you said, with potentially less cost-intensive piping infrastructure, and then also greater energy efficiency in terms of loads offsetting each other, even at lower heating load densities.
That makes sense. Excellent. Okay, well, we're running up to the end of the hour here. I think we might end about 1 or 2 minutes early, but thank you so much to our presenters. Those are both very interesting presentations.
Yep. Thank you.
Yeah, thanks very much.
And thanks for inviting me.